Thank you very much. It's a great pleasure to be here. I'd like to thank the organizers, especially Elizabeth Donnelly, for putting this very nice meeting together. It's the first I've ever come to, and I've enjoyed it very much. I'm going to talk about Axion detection. There is a connection to this workshop in a couple of ways. This is a collaboration. University of Washington is the lead institution, Florida, Livermore Labs, Berkeley, Los Alamos, and NRAU, so single people there. So I'm going to have a brief discussion of dark matter in the universe and a brief review of what an axion is as a dark matter candidate, how it might be detected, the experiment as it's been built and operated, a high resolution experiment which has some technical challenges, higher magnetic fields, and then multiple cavities, which I guess is why this is in this cavity session. So what is the dark matter problem? The dark matter problem is that there's more mass in most galaxies than the luminous matter. So you count the stars, look at the light, you get some mass from all of that, and it's not enough, especially to explain the dynamics of the stars moving around the center of mass of the galaxy. This has been known for almost 80 years now. Famous names like Oort and Zwicky. This is an example of the sort of measurements that one makes. You measure the rotational velocity, just the sideways motion. If the galaxy were mostly the stars, the stuff in the middle, then as you go out some distance from the center of the galaxy, the sideways velocity should fall off. That's what happens in the solar system. Pluto moves about 18% as fast as the Earth does in its orbit around the Earth. But instead what you observe is that the rotation curve is flat, and that means as you move out you're integrating more and more mass inside your orbit, and the halo mass alone accounts for most of this velocity at large distances. So this is sort of a cartoon of the galaxy side on. We're sort of here, and then there's this, it's called a halo, and I always think of a halo as a circular ring around a saint's head, but in fact it's a cloud whose density falls off with distance in such a way as to give this rotation curve. You can give it as a problem to your graduate students in the qualifying exam if you want. There's other evidence. Here's two galaxies that have collided. The ordinary matter, baryonic mass, protons and hydrogens and stuff, is here by measurement, and the dark matter has gone on further because there's viscosity or damping of the ordinary matter, but the dark matter just passes through itself without slowing down. And in fact, measurements by WMAP and later by Planck have turned on what they call the age of precision cosmology. Namely, they claim to know that 26.8% of the universe is dark matter, 8.3% is dark energy. We have no clue what dark energy is. We have candidates for dark matter, but we actually don't know. And then about 5% is the ordinary stuff that we're made of, protons, electrons, neutrons, and so forth. Only about 1% of the total mass energy is what you see. There's a fair amount of invisible ordinary matter as well. So I'm going to talk about dark matter, and there are a number of candidates proposed for dark matter. Neutrinos, we know neutrinos exist. And so they could, and we know they have mass, so they could be the dark matter, but they're typically relativistic particles. So when neutrinos are made in nuclear reactors and elsewhere, they fly out at nearly the speed of light. They're not cold. I mean, their velocity is not small compared to their rest mass energy, small compared to c. And so it's hard to make the structure of the universe as we observe it in models that use neutrinos as the dark matter. WIMPs are weakly interacting massive particle. That's another hypothesized candidate. People look for them. And then axions, that's the candidate that we look for. So what is the axion? They're actually not originally proposed to be dark matter. They come from a problem called the strong CP problem in quantum chromodynamics, the theory of the strong interaction, the theory of nuclei, basically the theory of quarks making up protons and neutrons. It's a theory that was developed around 1973. It's been well recognized. QCD, as is written, violates C, P, and CP, their product. These are charge conjugation and parity. The weak interactions are known to violate them. That's experimentally observed. But experimentally, the strong interactions conserve P and CP very well. And so there's a mystery, in some sense, in the theory that CP violating and experiment shows that it's not to the accuracy of the experiment. And the simplest way to state that is that if CP violation in the strong sector occurred, the neutral particle would have an electric dipole moment. We know that it has a magnetic dipole moment, but it also would have an electric dipole moment. So people look and measure the electric dipole moment of the neutrino, and it's about 10 to the 11 times smaller than a naive prediction, 1 e per neutron radius. Now we know the neutron is made up of 3 charged particles. Overall sum is 0, so you would think, just like water, there would be some dipole moment, but observationally not. And so that was called the strong CP problem, and the best solution to date is one done by Pecci and Quinn that postulate there's a hidden symmetry to the Lagrangian of QCD, and it's adjusted in such a way as to make the theory CP conserving. So another term is added. The potential is sort of a Mexican hat, is what the theorists like to say. So there's an order parameter. For those of you who've had superconductivity, this is a lot like the Ginzburg-Landau theory of phase transitions. We're below the QCD phase transition, so the order parameter is a finite value. Here's the origin here. And the phase of the order parameter in the bottom of this Mexican hat would be CP conserving, CP violating except at certain values, say 0. And so the hat is tipped up a little bit to a CP conserving value. And as soon as Pecci and Quinn postulated this broken symmetry to conserve CP, Weinberg and Wilczek independently and simultaneously noted that this requires there to be a particle associated with that. And the basic idea is if you have a potential, you can have a field that oscillates in the harmonic potential as the Mexican hat is tipped, and that oscillation gives mass to a particle, which they named the axion. And so the strong CP problem, if you use this solution, requires there be an axion. So the axion idea is now 30-some years old. At first it was thought it was relatively heavy, and you would look for it in reactors and beam dumps at accelerators and so forth. People looked and didn't observe it. The suggestion was then that the axion is very light, so-called invisible axion. It's similar to a neutral pion in that it decays by 2-photon emission, and the 2 photons come out cross-polarized because the interaction has an interaction constant G, axion density, E dot B in the Lagrangian or in the field equations. And so 2 photons come out back to back to conserve momentum and energy. But the half-life for decay is 10 to the 42 years for the invisible axion. That's why it was called invisible. It's so weakly interacting that you would never observe it. Theorists thought this was an ideal situation, a particle with no observable consequences. The coupling constant is proportional to the mass, so as they get lighter and lighter, they get weaker and weaker. About 1984, 85, it was suggested that axions could be the dark matter. And so here's the dark matter now hypothetically composed of axions. With the light mass axion, sort of microeV for MC squared, the number density in the halo is 10 to the 14 axions per cubic centimeter. So in 1 cubic centimeter in this room right now, there are 10 to the 14 axions, and in every other cubic centimeter, the same number. There are other ideas in the field. Axions or bosons, and they can Bose condense, and in fact, they should be Bose condensed if they're in thermodynamic equilibrium because they're so cold and the number density is high. And if you have a high density of slowly moving bosons, they have to Bose condense. The experimental case is in some sense stronger because the lightest supersymmetric partner has not been discovered at the LHC, and WIMP searches are not observing WIMPs and pushing down the boundaries of the WIMP interaction. So there's sort of a window for the mass. The mass could be anything because it's a free parameter in the theory. Here's the mass on the middle scale. I'll start with heavy axions, KeV or MeV, comparable to an electron. Laboratory experiments, the evolution of stars, other detection experiments, the duration of the supernova in 1987 have all been used to set limits on the mass and the coupling constant of the axion. And so there's sort of a heaviest axion might be a few milli-electron volts by these theoretical computations. If the mass gets too light, you create axions during the Big Bang, and you would create too many. So the lighter the axion is, the higher the mass density created during the Big Bang. And that sort of puts a softish limit down around the microvolts. So the light axion was thought to be invisible. It had no experimental consequences, penetrates matter, lasts forever. Only its gravity, of course. And then Pierre Sikivie, a colleague of mine in Florida, made them visible again. Now I told you that the decay is 2 photons with the photons coming out back to back. That's what happens in empty space. But if you supply a strong electric or magnetic field, magnetic fields are easier, that you can think of as a virtual photon. It's actually a very large number of virtual photons because it's a zero frequency field. So you put 1 photon in by hand, you stimulate the decay to a second photon. That second photon carries away mc squared plus the kinetic energy of the axion. So this is the Sikivie detector invented in 1983. It's called the haloscope. If you heard Budka's talk this morning, he also talked about other methods using the same principle. Static magnetic field stimulates the conversion of axions to photons. And so here's a big magnet, a solenoidal magnet with a vertical magnetic field. You have a microwave cavity. You choose the mode with a vertical electric field, a TM010 mode, say, that has good overlap with E dot B integrated through the cavity. And you'll get a single real photon. You put an antenna in the cavity, suck some energy out. You have a low noise amplifier. You mix down to an intermediate frequency, you mix down again, and you can then look at the output of the cavity over, say, a 30 or 40 kilohertz bandwidth. We actually do 2. I'll talk a little bit first about the so-called medium resolution. The standard velocity we have around the center of our galaxy is 0.1% of the speed of light. We're moving at c over 1,000 as we move around the galaxy. And so the axions would have similar kinetic energies, and so c squared, 1/2 mv squared, winds up being about a part in 10 to the 6th of mc squared, the rest mass energy. So that's what you sort of expect. And at a gigahertz or so frequency, you want to then look at about 100 hertz, 1,000 hertz spectral resolution to resolve this peak. But it's possible there's very fine structure, so we also do a higher resolution, 0.02 hertz. And the basic idea, it's like if you're driving across the desert in the middle of the night, trying to stay awake, and you try to find a radio station on the AM band, you tune and you listen for a while, and then you tune another 10 kilohertz and you listen until you find something. And so we're stepping through 30 kilohertz at a time a few tens of about 10 gigahertz all told, we'd like to do listening for the Axion. The signals are very weak. So the theory, the standard theory, predicts a power of about 10 to the minus 22 watts in the situation where the cavity volume is 200 liters, the field is 8 Tesla. There's a form factor, which is the integral of E dot B over the cavity. That's the C here. There's a coupling constant. There's sort of two theoretical coupling constants that differ by about a factor of 3, but we square it, so their strengths differ by about a factor of 10. The Axion density, which we take this to be at our point in the galaxy, the mass, and then the Q of the cavity. So there's a resonant enhancement by putting it into the cavity. The Q could be the width of the Axion, this kilohertz bandwidth of the Axion, but in fact, it's always the Q of the cavity, about 70,000 for copper at helium temperatures. So there's the cavity. Q, actually unloaded Q was up to 200,000 in our best cavities. Here it is in a vacuum can in an insert. There's a helium with a magnet in there where we have our SQUID amplifier, a couple of students. And then this whole thing is put inside an 8 Tesla magnet. This is the magnet cryostat being installed a number of years ago. We look over a spectrum, and I just show the spectrum we're looking at. Up till now, it's been between about 500 megahertz and a gigahertz. And our plan is to go up to 4 or 5 gigahertz. The Axion experiment has gone through a number of generations of upgrades. So we started out with the cavity I showed you and using cooled gallium arsenide field effect transistor amplifiers. Those had noise temperatures of around 2 or 3 Kelvin, and we operated at a physical temperature of around 2 or 3 Kelvin, and so we had a system noise temperature of around 5 or 6 Kelvin. That was the background, the thermal emission from the cavity and the excess noise of the amplifier. About 5 years ago, 6 years ago, we converted to superconducting quantum interference devices, SQUIDs. You can get gain from a SQUID, RF gain from a SQUID. John Clark at Berkeley developed these. And these have very low noise temperatures. I'll say a little more about that. And at present, we're reducing the temperature. We started a few years ago designing and ordering this, but there's a dilution refrigerator, helium-3, helium-4 mixing chamber at the bottom here that will cool us to about 100 millikelvin. The SQUIDs are wonderful amplifiers. A SQUID basically measures the flux in a superconducting loop, and it diverts current between one or the other of these junctions depending on the flux. And you get a voltage, therefore, associated with it, so the output voltage as a function of flux is a sinusoidal. And so there's a transfer function where you can have gain. If you modulate the flux, you modulate the output voltage. And the trick that Clark came up with was to, instead of having a transformer here, he has a strip line. The microwaves run around on the strip line, reflect off the end, and come back, and that affects the transfer function of the oscillator, and you get gain. And so here's a gain curve, sort of 10 dB with a peak of over 30, and really good, and you can see it's got a reasonable bandwidth, but not a huge bandwidth for a measure. This is the measured noise temperature of a SQUID as a function of the physical temperature from 4 Kelvin down to 20 millikelvin. And it's pretty flat at the lowest temperatures and very close to the quantum limit, where KT would be h bar omega for the measurement frequency. And then as the temperature comes up, the noise temperature also comes up. So at around 100 millikelvin, we can expect 80 or 60 millikelvin noise temperature in the SQUID and 100 millikelvin excess temperature emitted from the cavity itself. And so we're looking for less than 200 millikelvin. And that, of course, increases our measurement time. As the signal background noise goes down by a factor of 10, our measurement time goes down by a factor of 100 because we're just integrating up noise and signal. The basic design is a little complicated because of the SQUID, because the SQUIDs don't like magnetic fields. That's what they sense, is magnetic flux through the SQUID loop. And so we have to have it in a field-free region, and we do that with another smaller coil of about 4 Tesla sitting up above in this helium reservoir. And then the cavity is here. There are tuning rods, so the cavity has to be tuned. And the way we tune it is to move a metal rod from the wall, where it has basically the frequency of the empty TM010 cylinder, to the center, where it has the frequency of a TEM cavity, I'm sorry, of a coaxial cavity, still TM mode. And that tunes by about a factor of almost 2 if we use large enough tuning rods. We use 2 of them, in fact. So there's another picture of the dilution fridge. It goes in between the bottom of the helium reservoir containing the bucking coil and the top of the cavity. This is the world's quietest receiver. So if you integrate for a while, your noise temperature is about 10 to the minus 26 watts. You can detect that power above background. Integrating for, I guess we integrated for several hours, 30 days, I'm sorry, 30 days of integration. So how sensitive is that? 10 to the minus 26 watts is 1/100th of a yoctowatt. Yocto is the smallest prefix you can find in the SI dictionary. Corresponds to about a photon per minute. So imagine you had one of these in your cell phone. You could take your cell phone to Mars and turn it on, and you would get 4 bars from a station on Earth. So it's a pretty sensitive receiver. An Axion would look like a peak. This is a simulated Axion that was injected as part of testing our data acquisition system. And as I say, in one of the spectra, it would always be at this frequency where this h nu of this frequency equal to mc squared of the Axion. And so that's sort of what we look for. Here's some real data, and there are actually candidates in both of these. So we scan about 30 kilohertz around the central frequency of the cavity, then we tune it by about 3 kilohertz and scan again. Each of those spectra took about 30 seconds to take, say, 50 seconds to take. Here there was a peak in a number of the scans. It actually went away as we came closer to this frequency being on resonance. It was a radio signal that was being picked up and then reflected from the cavity. As we came to resonance, that energy actually got dumped in the cavity and partially absorbed. So the radio signal was stronger here than it was on center. Here's a peak that showed up in the combination of a bunch of spectra, but was not visible in any single one. It's a statistical peak. So we do see candidates from time to time. How do we determine that they're actual candidates, false signals, and not Axions? Well, we go back and look again. If it's statistical, it goes away very quickly. If it's radio, we have a veto channel with an antenna, but the simplest thing we can do is turn down the magnetic field. Since the power goes as the square of the magnetic field, if we turn down the magnetic field and the signal persists, then it's not an Axion. So no detections yet. We've scanned this range in frequency from about 400 gigahertz to around 800 gigahertz. And we've done it with enough time and signal to noise to rule out the stronger of these 2 model G factors that I told you about, the one that was 0.97. We intend to get enough sensitivity with the dilution fridge to rule out the weaker of the 2, and so essentially the whole range of standard model Axion parameter spaces between these 2 lines here. Over a period of about 5 years, one hopes to go from a frequency of about 400 megahertz to maybe 4 or 5 gigahertz. Let me turn now to this high resolution spectrum. The idea is could there be sharp features in the Axion spectrum? The Axions are cold particles. They're created more or less at rest at the Big Bang, and they've been sitting in the universe ever since. And they form the halo of a galaxy by having mass fall in from intergalactic space into the galaxy. And of course, each particle that falls in falls along the gravitational field of the galaxy towards the center, and some of them come past Earth. This one comes past Earth on its way in. This one comes past Earth on the way out. the galaxy is continuing to accrete mass, and so they never get out if they fall in from rest. They'll fall through, almost leave, and then bob back and forth, or if there's angular momentum, they'll follow some spiral path. So if they come past us from a well-defined position, they come past us with a well-defined velocity. So they all have the same kinetic energy. So the velocity might be, spread of velocity 1/2 mv squared might turn out to be 0.02 hertz out of a gigahertz. And so our high-resolution channel looks for sharp peaks from late in-fall axions, as well as the broader search looking for the Maxwellian contribution. This one would just not resolve these sharp features, of course. The high-resolution data, again, occasionally sees candidates. This is a spectrum from 499.98 or 975 out to 500.0035 megahertz. And we can see occasionally these radio signals both in the high resolution and the broader medium resolution search. And so you can set a limit by assuming some model of the infall, but this is really a discovery mechanism. The fact that you can concentrate all the energy into a very narrow bin means you've reduced the noise, because the noise is constant per root hertz, and so the signal to noise should be better, assuming that such sharp features appear. So the high resolution search just does the same thing as the medium resolution. After a couple of conversions, we do a FFT of, let me say, 100 seconds of measurements over 50 kilohertz bandwidth, so about 10 million points. That gives us 0.02 hertz spectral resolution. And one of the issues is the phase noise in the local oscillators, which is the subject of some of the vendors and some of the talks here. They have to be good enough to maintain this signal for over 100 seconds in one bin of our FFT. We have to stop after about 100 seconds because the Doppler shift due to the Earth's motion, our rotation, we're circling around. Unless we're at the North Pole, the detector is on the surface of the Earth and it has a velocity which is changing every day around in a circle. And so that Doppler shift blurs the signal after about 100 seconds at the frequencies we're at. Okay, so now let me turn to third generation. How am I doing for time? 12, including the questions. Okay, this will be easy then. So we're now considering a next generation Axion detector similar to ADMX and trying to write design specifications and rules and see what one can come up with. And of course the top level requirement is we have to be sensitive to the most weakly coupled axions and be able to detect axions with mass in what I call the sweet spot. I'll show you that in a minute. With measurement times and scan rates similar to the current ADMX. Here's the sweet spot. So we're looking here with mass frequencies between 400 and 800 megahertz, or masses between about 2 point something microeV, 3, 4 microeV. And we're intending to go up a little higher, but if you go back to the standard model, go back to the QCD prediction and say the halo density is what it is, the axions form 0.23 or 0.26 of the mass energy density of the universe, then you get a prediction for the mass. And that prediction is about 2.5, I'm sorry, around 20 or 22 microelectron volts. And so a frequency of a resonant cavity around 4 to 5 gigahertz. So we should be looking there. So this is like the drunk looking for his keys under the light post. The policeman asks, where did you lose your keys? Over there in the bushes. Why are you looking under the light post? Well, the light is better here. Okay, our cavities work better and our sensitivity is better here. Suppose we'd want to just go up from 500 megahertz to 5 gigahertz. What do we have to do? We have to make cavities that resonate at 5 gigahertz. Those are smaller. Remember that the power from the cavity has in it the volume of the cavity. So if we make the cavities 10 times smaller in all dimensions, we're giving up a factor of 1,000. B comes in squared. So the experimentalist has control over these two things. A little bit this by choice of the resonant mode. Nature tells us most of the other things in here. And so we'd like to maximize B squared V. And so if we're going to go smaller in volume, we need to go bigger in field. That's sort of the bottom line for this. The simplest cavity is a right circular cylinder. One can make much more complicated structures, make periodic arrays of posts, put vanes in that steer the electric field around in the cavity. We're actually exploring some of these approaches, and we're finding it's a nightmare because the TM010 mode can be high in frequency and can tune the way we want it to. That's the one that couples to axions, but there's a forest of other modes. There are none of them strictly TM or TE in these complicated structures. But, and every time a mode crosses, of course, you get mixing and you lose sensitivity. So mode crowding by having even very long cavities that are small in diameter is an issue we have to address. So as I say, if we want to go with a simple cylinder like this to 4.5 gigahertz, we wind up with 2.6 centimeter. The cavity can't get too long. Here's a tuning experimentally of a cavity of about that frequency. The TM010 tunes from 4.5 gigahertz down to 3.4 gigahertz as we move the tuning rod from the wall to the center. But you can see these TE modes exist, and every time a TE mode and a TM mode come together, we have trouble. We have to do something to walk around that resonance. And if the cavity is longer and longer, the TE mode spacing gets shorter and closer together. So we try not to make them too long. The power will then decrease with frequency. So here's a simple calculation of how it would go if all we did was take one cavity, put it in, make it smaller, put the next one in to go to the next frequency and so forth. You lose a signal like f to the 2.67. That comes from the volume. There's a little bit of gain. There's a single power of f gain, and the conversion factor as the mass of the frequency goes up. And then there's a problem with the Q. Even though we're in the anomalous skin effect limit, we have a Q that decreases as f to the minus 2/3 as we go up in frequency. So B squared V is the factor to maintain. One fact that we have is that right now we have, because we have 4 bars on Mars, 3 or 4 times more sensitivity than we need for the measurement strategy or the measurement cadence that we take, about 100 seconds for each setting of the cavity. We don't want to go too much faster than that because it takes time to tune the cavity. You have to let the heat escape after you've jogged the tuning rods. You have to measure the frequency and then turn that off and let that ring down. So it's not possible to scan at a really high rate by the methods that we use in Inigum. So you can go big in volume or big in field, of course, to maximize this. There are big magnets, and people are looking at acquiring maybe 8 Tesla magnets that are 5 or 6 times bigger than the 50 centimeter diameter, 1 meter long bore cavity we need. But we think it's desirable to reduce the volume and increase the field. 26 Tesla is now available. The magnet lab is making a 26 Tesla magnet. So we can gain a factor of 10 there and lose a factor of 20 in volume and maybe use multiple cavities. So let me jump over the argument about fields. Here's a design with a 0 field region that would work here. So the other approach, other contribution or step that needs to be taken is to use multiple cavities added in phase. And so this is just a little experiment where we tuned 2 cavities, showed we could add them in phase. And the basic way to tune them is to use some sort of Pound-Drever Hall or pound locking, reflection locking of the cavities. And so we're in the process of taking a look at reflection locking to basically you measure the phase on reflection of sidebands and the carrier, and you get a linear error signal in the end for measuring them. So this is our simulated signal for that. And I had hoped that we would actually have some results, and my student says we're close, but we don't. And so then each cavity could be part of a servo to drive it to some resonance. Okay, so summary and conclusions. Attractive dark matter candidate. Their searches, ADMX is one. There are actually other searches ongoing away that are sensitive to realistic couplings and masses. Could see the axion at any time. And future experiments will need higher fields and multiple cavities. Thank you.